In this session, we're going to discuss secant method. The Newton-Raphson algorithms requires the evaluation of two functions, the function and its derivative, for each iteration. If they are complicated expression, it will take considerable amount of effort to do hand calculations or large amount of CPU time for machine calculations. Hence, it is desirable to have a method that converges as fast as Newton's method, yet involves only the evaluation of the function. So let's have this graph. Okay, so let x sub 0 and x sub 1 are the two initial approximation for the root, okay, of function at x equal to 0. So this is our function, and we want to determine this root, wherein function at x is equal to 0. Okay, and by evaluating this, we also have the function at x sub 0 due to the initial guessed, and function at x sub 1 same as with the initial guessed. Okay, so these are the three functions that we need to evaluate using secant method. Okay, so if we're going to draw a line between the function x sub 0 and x sub 1, it will intersect to our x-axis. So this will be considered as x sub 2. Okay, and as you can see here, okay, since this is 0, x equal to intersect with x, so it means somehow it's nearer to our root. Okay, so if we're going to repeat this solution, there will be instances it will converge to our root. Okay, so what is the equation that relates x sub 0, x sub 1, and x sub 2? So using the slope, okay, which is m, we could derive the equation or the relationship between these 3 points. Okay, we all know that from x sub 2 to x sub 1, we have this slope. We all know that slope is the rise versus fall, the rise divided by its rise divided by run. So the rise is based on function and the run is based on the x value. Okay, between these 2 points, x sub 0, x sub 1, the rise is function x sub 1 minus function x sub 2 all over the distance between 2 points, x sub 1 and x sub 0. And for x sub 1 to x sub 2, we have the same root since a same slope rather, okay, because it's just continuation between from x sub 0 to x sub 1 to x sub 2. So therefore the slope is the same. So we could say that it's equivalent to the slope of between x sub 1 and x sub 2. And same concept, rise divided by run. So the rise will be function x sub 2 minus function x sub 1 all over the run, which is x sub 2 minus x sub 1. Okay, and we all know that function at x sub 2 is equivalent to 0. Okay, we assume that it's equivalent to 0. So therefore, when we evaluate this portion of our equation and this equation, so we're going to transfer x sub 2 minus x sub 1 to the left side and this equation to the right side, and the result will be this. And then we're going to solve for x sub 2 since this is the nearer to the root. Okay, so every time if we want to get the root, so we're going to solve for the x sub 2. So transpose x sub 1 to the right side, we have this equation. Okay, so it means this is our working equation for secant method. Okay, so to generalize the formula, okay, so this will be our equation. x sub I minus function of x sub I times x sub I minus x sub I minus 1 all over function of x sub I minus function x sub I minus 1. So x sub I minus 1 is the first value that you've declared. X sub I is the second value. Okay, and then the x sub I is the result of the first two values. On the next iteration, the x sub I plus 1 will be your your previous x sub I will be the x sub I minus 1 for the second iteration, and the current x sub I plus 1 will be the x sub I to the next iteration. Okay, so that is the algorithm behind secant method. So this is easier compared with the Newton-Raphson, because in Newton-Raphson, again, we need to define the first derivative, but here we're just using the function to define the approximate root. Okay, so let's have an example.